Yes, it's starting.
Okay, so I change a bit the title, as you might see, so the journey will be a bit shorter. But when I tell people that I'm doing mathematics, it's quite not unusual to get a very strange look, and then the people say, mathematics has always been scary to me. And actually, what's the application of doing pure mathematics? There is a very easy answer to that question, which is that basically all our technology depends on mathematics. And at the time they discovered it, the people had no idea of the application that it would have decades later. But there is much more to it. And in my opinion, it is very cool that mathematics allows to go to the moon, but it is also about discovering concepts that impact the way society thinks. And in my opinion, it is as important as the productionist answer. And I would like to give 2 examples of that here. So to do that, let's go back to middle school for a moment and do some geometry. So you have learned about triangles and some of their properties, like the fact that the sum of the 3 angles is always 180 degrees. Also, if you draw a line, like the green one, you can always draw another line, the blue one, which do not cross the first one, so it's a parallel. This is always true, right? But is it really always true? The question goes back to Euclid in ancient Greece. He wrote about the basic postulates of geometry. And one of the big questions was, can we deduce one postulate or one axiom from the other ones, like the one of the parallels? To figure out, let's take a spaceship and an animal, like Annette did at the last Sin, and we send it to space. And what would our monkey see? Actually, it would see that the Earth is round. And there, the rules are very different. For instance, you can now draw fat triangle. That means that the sum of the angles is higher than 180 degrees. Very weird. Also, there is no parallel anymore, because if you take 2 straight lines, by a straight line I mean a curve that is the shortest path between points, those straight lines, they will always cross, like on this picture. So no parallel anymore. This is the discovery of non-Euclidean, remember Euclid, non-Euclidean geometries. And they were very useful, for instance, to understand Einstein's relativity. But they had also some impact on Cubist artists. People like Marcel Duchamp and Jean Metzinger, they would learn about those geometries from mathematicians, friends of them, and they would think that if even mathematicians, you know, those very rigorous and serious people, if even them, they play with fancy and very weird geometries, there would be no reason for those artists to stick to the basic rules of perspective from Renaissance. So here is another example of the kind of applications of mathematics. Here it gives some legitimacy to artists to investigate into cubism in this case. Okay, now let's go back to Earth and try to draw a map of the Earth. So the weird phenomena we encountered before comes from the fact that on a sphere there is some curvature. And here comes the math again. A theorem tells you that there is no way to accurately draw a curved surface on a flat one, like a map. And this you can see on the Mercator projection, that it is wrong in many ways. For instance, the shortest path from New York to Paris, it is not the straight line, the red one. It is something like the curved green one. Also the Greenland, it seems to be the same size as Africa, which is obviously wrong, right? And this is some bias given by the map, and which favors actually Western civilizations. And let's try to fix that and look at another map where now the relative size of the countries are respected. So now it takes into account Africa's importance, but as you can see, the shape of the countries are completely distorted. So here, the mathematics, they show us that we need to make some choices while representing the world about what to keep right and what we allow to be wrong. And those choices, they inherently introduce some bias in our perception of the world. All right, thank you. Sure.
What is your favorite map of the world? Favorite?
Actually, that's a very good question, and I guess that my answer would be that there is no best one, in the sense that you have to know the curse of each one and deal with it the way you want. So, for instance, the Mercator, so that's the previous one, it respects angles, so it was very useful for sailors, because what they wanted to do is to take their compass and say, if I go this direction, I will end up in New York. So if they leave Paris and they follow the red line, that is the line they would follow with their compass. So for them it was very convenient to use this one. So it really depends on what you want to do. You will pick up one or the other. Yeah.
Along those lines, one projection came out relatively recently. It's either the die, something with an accident, or the butterfly one.
That might be. I don't know it.
Okay, it's supposed to be the best one or something like that.
Okay.
It doesn't tell the north though. The problem with it, the dimaxic.
Oh, so
projection,
it's something like this,
it's
or
like taking the Earth into an icosahedron and flattening it in triangles so that it spreads out. It was done by Buckminster Fuller.
okay.
Oh, okay, then maybe the butterfly one is the more recent one.
The butterfly one is very short.
Yeah.
Okay, but what's also interesting is to see how they are built, and so then you understand also the distortion you have. So how do you pass from the sphere to this one or the other one? So what does it mean to project, and what is the actual construction that you are doing? And it's pretty nice to see. Yeah.
So if you look at a globe, like the 3D globes that people have as maps, traditionally were those the sort of straight 2D image then wrapped and stretched around the globe? Like, would they be accurate? How long ago did they become actually accurate?
Okay, so I think the way it is done is not to take a flat map and to make it round. So it should be the most accurate representation of Earth. But how it is done is to so actually here the problem is that you want to map the whole world on at once, and so you get very big distortion. But if you focus on one specific point, then it is on the sphere almost the same as on the plane. And so that's how you would do a globe. You would work very small piece by very small piece to put them together. And so you don't really see any distortion. Yeah?
So from 2D to a globe seems like it makes sense, but then you had the hyperbolic plane there. Can you talk a little bit more about that?
Yeah. So can you? So actually, the problem is exactly the same. So you would also have to choose between. So no, it's a bit. Yeah, back. Yeah. The next one. So this is some. So you have different kind of non-Euclidean geometries, and this is some hyperbolic geometry, and the difference is the curvature there. But you would have exactly the same problem. So you would have to choose between having the angles right, or having the relative size right, or.
I guess I'm asking, under what circumstances might you expect to encounter a hyperbolic geometry?
Oh, okay. Well, that's an interesting question. In physics, in relativity, there you encounter some hyperbolic geometries. The fact is that the idea is that you don't have to to look at the time and the space as separate entities, you have to look at the whole. So that's why we talk about 4D, four-dimensional space, because you have 3 for the space and 1 for the time. And all are mixed together. And the way they are mixed is as a curved space, and you can encounter some hyperbolic geometry there. So, yeah.
Okay, I don't know if I'm going to formulate this question correctly, but like, how does this affect sort of physical phenomena that we usually, like in school, use like vector analysis to study, like so like force, for example, like on a page in school we like the straight line, but does this affect like that on Earth if you're like studying what force is on Earth?
Okay. I'm not sure what's the best way to answer that. But
How about gravity wells?
yeah, so as you say, again in general relativity, so that's the theory of Einstein, but where you look at gravity. The whole point is that energy, so mass, for instance, it would curve the space, and the idea of general relativity is that that gravity is not really a force. Actually, it is just that objects, they move the way they move because they follow the curvature of space. So the reason why the Earth loops around the sun is not because there is a force between the sun that attracts the Earth, but it is because the mass, so the energy of the sun, it deforms the space around it in such a way that if the Earth tries to go straight, she would actually follow the curvature of that space, and that curvature is this loop around the sun. So I don't know if it makes sense. Exactly. So maybe you've seen that experiment where you take some elastic sheet and you put a mass in the middle, so it would make some kind of well here. And if you drop a ball, it would do this kind of trajectory towards the center. That's exactly the idea. The ball would follow the curvature of the well, and the idea of relativity is that it's the way it happens in our space-time.
So to tie those things together, maybe where the ball is on that well, if you were going to calculate force on that, it would be
It would eventually be a straight line.
yeah, it'd be relative
It would be
to.
more like the
Sorry?
No,
non-euclidean.
is
Jiggy
that
and I are
what
trying
Okay.
to get what you actually do. Putting our heads together.
But it's yeah. So it's really the importance of the straight lines, as I said. So can you go back? Yeah, there. So I said that any two straight lines, they would cross. But you might say, no, right? If I just drove here the circle like this, it would not cross the green one, so I would win. But actually, it's not a good answer, because this circle, it's not a straight line. It's not what we call a geodesic, in the sense that if you take 2 points on that circle, the length of the curve between them, it is not the minimal one. The minimal one, it is always the one given by those big circles that have the center, whose center is the center of the sphere. And if you draw those big circles, they will always cross at 2 points. Okay. So you see that a line, a straight line, it's not just any line in the space. And this is really linked to the curvature. Yeah.
So in terms of mathematical research that interests you, am I guessing that geometry is one of the areas that you're interested in?
That's right. And so Actually, so my first title was from a flat world to a quantum one, and the curved one was just the intermediate step. And the quantum one, it is the geometry that you encounter when you look at very, very, very small scales, like the one of particles, like electrons. There you have quantum mechanics, and in quantum mechanics it tells you that the object, you cannot specify all their properties precisely all together, like position and the speed of an electron. You cannot measure that very precisely at the same time. And it's not because you are not smart enough to build a very good machine, it's really because intrinsically the electron, it does not have a position and a speed well defined at the same time. And so the kind of geometry you have to use to describe this, this is called non-commutative geometry.
More precisely, when you look at the electron, so you are shooting a photon at it. Once both objects are so small that when one hits the other, you don't know the position or the momentum, or so you lose it.
Right, but the point is that it's really because it's really intrinsically in the nature of the particles, and so you have to use another language to speak about those objects, and so this is another kind of geometry.
It's called an isometric.
Yeah, that's for quantum mechanics.
Did Euclid ever think about geometry beyond 2 dimensions? I mean, did he never take his piece of paper and wrap it around a ball and say,
Can you repeat the?
did Euclidean geometry, he described it was purely 2-dimensional. So did Euclid theorize about anything beyond 2 dimensions?
Actually, Euclidean geometry can be any dimension because you can talk about lines. Okay. You're right. If you just speak about parallels, then you have to stick to 2-dimensional. But so your question is that
Mostly just in one of the slides you labeled Euclidean as like a plane.
yeah.
And then you had other things that were non-planar. So I was just wondering, like,
Okay.
what was the extent of what's described in his?
Okay, so the next slide, this one. Actually, so you're right. You've got the impression that this is 2-dimensional and this is 3-dimensional. Okay, but in fact, this is also 2-dimensional in the sense that it is a surface. But for us, we have to see it in 3 dimension to be able to represent the curvature. Does that make sense?
But in Euclid's writings, did he cover anything other than the strict
Okay.
two-dimensional plane?
I'm not sure. I'm not sure. I have to admit I haven't read but I will. But what's interesting is that actually you don't need the 3rd dimension to describe those surfaces, even if they are curved. So for instance, the 4th dimension of space-time, you might say that because they are curved, we have to need a 5th dimension to see that curvature. Actually, it's not the case. Mathematically, you can describe it really intrinsically, and you can even measure the curvature from the surface without going out. So,
I'm going to go out on a limb and say that I think that Euclid talked about solids, but in a Euclidean space. So,
yeah.
what is the volume of a cone? What's the volume of a sphere?
Mm-hmm. But I'm not sure about the axioms. They're the well-known Euclid axioms. No, but it's right. I think it's okay for any dimension.
What do you personally apply this to when you're working, when you're in your life? What's the practical?
Okay, so one of the questions, so I said that the geometry in the very small scale, let's call it quantum geometry or non-commutative geometry, to make it a bit more scary. So that is the geometry of the very small, but we don't see any quantum thing at our scale. But still it's the same world, right? The world of the electron, it's supposed to be the same as mine. So how do you understand how to pass from our scale to the very small scales? And that is also a question you can ask in mathematics, how to deform one space to the other. Like, you could see that there is a very big difference between this, which is curved, and the plane, which is flat. But if you deform slightly this one, you stretch it, you can make it look more and more like the plane, right? So you don't see the curvature anymore. And that's the idea of deforming this space into the flat one. So the flat one would be a limit of this one as you deform it. Okay, the deformation might be, for instance, if you zoom in here, you see less and less curvature. Okay, same on the sphere. And you can ask the same about non-commutative geometry. How would you zoom in from one geometry to the other? And so this is called deformation quantization, and that's the kind of question I was interested in.
So would you say, in order to study quantum geometry, you could zoom in even more to make things look more flat?
Okay, that's a good point, because in this case, it is not about zooming. You have to deform something else, and so, but there, I think that there is not a very good answer. But so, yeah, maybe one way to answer is to say that one electron, that is a very quantum thing. But at our scale, we don't see any quantum effect. And one of the reasons is that there is so much particles that all the quantum effects, they average themselves, and so we don't see them anymore. Okay, does that make sense? So you might think, okay, the limit process is to add more and more electrons, and at some point, or electrons or any particle, and at some point, I will have enough of them to have a classical world where I don't see quantum effects. That's not quite right, because there are systems with a lot of particles, but that are in such specific conditions that you still see the quantum effects. So this is not a perfect answer, but maybe it gives you some insight of what you can do to deform in some sense, to go from quantum to classical. But that's a very, very tricky question, and I don't understand it fully for sure.
Well, thank you very much, Alban.